Welcome to This Explainer. Today we're diving into the incredibly high-stakes world of workplace electrical safety. Look, if you're watching this, you already know we interact with electricity literally every single day. It's so easy to get complacent, right? But the second we step into an industrial environment or start working directly on power circuits, that complacency, it can be instantly fatal. So, we're going to unpack the absolute definitive safety protocol that keeps electrical workers alive. We're talking the full, complete lockout-tagout procedure, breaking down every single step.
Let's just quickly run through the agenda. We'll start with the hidden electrical threat, then introduce lockout-tagout, walk through all 8 steps of LOTO, and finally look at exactly why we test and then retest. All right, Section 1, the hidden electrical threat. We're talking about the explosive stakes of electrical faults.
To really wrap our heads around the danger here, we got to look at a specific number from the NFPA 70E standard, 35,000. An electric arc flash can reach absolutely staggering temperatures of up to 35,000 degrees Fahrenheit. Let that sink in. It's almost hard to comprehend. You might be wondering, well, how on earth does it get that hot? The source material makes this really fascinating distinction. See, unlike your typical chemically driven fires, where the temp is limited by how fast the chemicals combine, an electric arc doesn't have that limit. The temperature is literally only limited by the rate of power dissipated in the arc. Basically, the more power feeding the fault, the hotter it gets. And at 35,000 degrees, the heat is so extreme, it instantly vaporizes the metal wires involved in the fault. Gone. The NFPA standard notes that these events are lethal up to 10 feet away. But here's the thing. The heat isn't even the only danger. The explosive expansion of superheated air, combined with the sudden disintegration of solid hardware, creates what we call an arc blast. Because it's an electrically driven explosion, an arc blast can actually be way more violent than a chemical explosion. We're talking a massive shockwave of deadly shrapnel.
Now, in those rare cases where completely de-energizing a circuit just isn't possible, workers have to wear specialized protective gear, like the heavy arc flash suits you see here. You'll notice the blue hood covering the head and neck and the heavy gray jumpsuit. These things are rated by calories, specifically the number of calories of heat the fabric can take before it breaks down, basically acting as a shield for your skin. But listen, while they do a great job protecting against the intense thermal energy of an arc flash, there is absolutely no suit in the world that can protect a human body from the concussive force and flying shrapnel of an arc blast. None.
Which brings us to Section 2, introducing lockout-tagout, the definitive solution for electrical safety. So the major takeaway here is that our very first and absolutely best line of defense against shocks and arc flashes is completely de-energizing the circuit. You have to remove the lethal energy entirely. By doing that, the circuit reaches an equipotential state with the earth, meaning there is zero voltage potential to harm you. And this leads us to the ultimate solution, lockout-tagout, or LOTO. It is a completely non-negotiable lifeline for anyone doing electrical work, making absolutely sure that power cannot be accidentally turned back on while someone is in the danger zone.
We really need to understand the sheer gravity of these procedures. Our source material has this incredibly grim but true reminder. All safety standards and procedures are written in blood. This is not just bureaucratic red tape, it's not some annoying checklist designed to slow down your day. Every single one of these protocols exists because someone got severely hurt or came terrifyingly close to it because they didn't take the right precautions. When we do a full LOTO procedure, we are literally honoring those hard-learned lessons.
Let's jump into Section 3, the 8 steps of LOTO. This is all about meticulous preparation for a zero-energy state. All right, let's break down the complete lockout-tagout procedure. We're going to cover all 8 steps. The first half is all about isolating the power. Step 1, you turn the equipment off using its normal on-off switch, which safely interrupts the normal load current. Step 2, open all disconnect switches or breakers that feed power to that specific equipment. Step 3, if the hardware actually allows for it, you visually confirm that all poles of the disconnecting switches are physically open. You really want to see that air gap with your own 2 eyes. And then Step 4, you attempt to restart the equipment using the normal controls. Pushing that start button and seeing nothing happen is your very first confirmation that the power is actually off.
Okay, now we move into the ultra-critical verification phase. Step 5, attach your personal locks and tags so nobody can reclose those switches. And hey, the source points out that if there isn't a lockable disconnect, you have to open and tag at least 2 redundant disconnects. Step 6, confirm your voltage meter is working properly by testing it on a known live power source. Step 7, test for dangerous voltage between all relevant conductors. That means checking phase to phase and each phase to ground. Finally, Step 8,
Take that exact same meter and reconfirm it on a known live source one more time.
Moving to Section 4, Why We Test and Retest, the twist of hardware failure.
You might be thinking, why all the redundant meter checks? Well, the reality is, test equipment fails. Multimeters and their leads aren't just handy tools. In a LOTO situation, they are literally life-saving devices. The author of our source material actually mentions having personally seen multiple cases where a test lead failed internally. Basically, the wire breaks inside the rubber insulation. When a lead fails open like that, your meter is going to read 0 volts, completely masking the lethal voltage that's still there. That is exactly why steps 6 and 8, verifying your meter on a known source before and after, are so crucial. You have to prove your life-saving tool is actually working.
And this right here perfectly illustrates why step 7, testing all those conductors, is non-negotiable. Look closely at this photo. It was shared by an electrician named Jim Lyon, who found this during a routine LOTO procedure. You're looking at the inside of a 3-phase disconnect switch. If you check out the mechanism on the right side there, you can see that the mechanical linkage between the actuating lever and the switch pole has completely snapped off.
Because that little internal piece broke, one phase of that circuit stayed completely closed and totally energized, even while the other two opened up just fine. The crazy part? To anyone standing outside, the external switch handle was securely in the off position. There was absolutely zero visual clue on the outside that the switch had failed on the inside. If Jim had just trusted that piece of plastic saying off meant 0 energy and skipped step 7, he would have grabbed a fully energized conductor. Just trusting the switch without doing a proper phase-to-ground test could have easily resulted in a fatal electrocution right then and there.
That broken switch, that is the ultimate proof that you can never, ever assume a circuit is dead just because you flipped a breaker. We test and we retest because hardware fails and the stakes are just way too high to guess. So I want to leave you with this final thought as we wrap up this explainer. The next time you're about to start some electrical work, are you going to bet your life on a simple plastic switch? Or will you follow the steps written in blood?